Okay, so this is an example of an open response question you might see on the AP test. So, here's the diagram. A spacecraft is in a clockwise orbit of radius r around Earth. The mass of Earth is me. In the figure below, draw and label the forces that act on the spacecraft. Each force must be represented by a distinct arrow starting on and pointing away from the spacecraft. So there is only one force acting on the spacecraft, and that's the force of gravity from the planet. And the reason that the spaceship is not flying into the planet, because even though there's only one force, is because it already has a velocity in this direction. So the force only serves to turn, and that's why it's in an orbit. Just to clarify, that's why there's only one force. And then here, derive an equation for the orbital period t of the spacecraft in terms of the mass of the spacecraft, the mass of Earth, the radius, and physical constants. So here I started with a few equations. F equals ma, that's just Newton's second law. Yeah, that's just Newton's second law. And then we have the force of gravity is equal to the gravitational constant times the big mass, little mass over the radius squared. And then we have this, which is the velocity is equal to 2 pi r over the period. This works because the units for velocity are meters per second, and the units for period are seconds, and this is just finding the circumference. And since the period is how many seconds it takes to do the full circumference, this is the equation that connects the velocity and the period. And then here we have the acceleration, the rotational acceleration is equal to v squared over r. So what we do first is we replace the acceleration with v squared over r, and then we replace the force of gravity with the gravitational equation. Then we can do some canceling out. We can cancel out the radius on both sides, and we can cancel out the little mass on both sides, and then we end up getting the velocity squared is equal to the gravitational constant times the mass of the Earth over the radius. And then we can replace the velocity with the equation so that we can get the period, because that's what we're looking for. So we replace the velocity with 2 pi r over t, and then we have to square that whole thing because the velocity was squared. So then we get this equation, and so I'm trying to keep it as neat as possible because this one gets a little messy. So we have we can multiply this r over here, this r squared. We can divide it from both sides and get the g times the mass of the Earth over r cubed is equal to 2 pi squared over the period squared. And then we move 2 pi squared over to this side, and then the problem is we have 1 over p squared, which doesn't work. So we flip both sides upside down. So basically we're just dividing both sides. But in order to keep it simple, I just flipped both of them over. And then we can take the square root of both sides. Since 2 pi is already squared, it can just be outside of the radical. And then inside of the radical is the radius cubed over g times the mass of the Earth, and that is equal to the period.